All right, folks. I'm going to give a little clarity for number 3 and then kind of get you started on number 4. This is coming off of KSP. And yeah, just to give you guys a second chance and a second look going home over the weekend to see the process of solving. Okay, so if we revisit number 2, what number 2 showed us was if we have KSP provided at a given temperature, they want us to determine the equilibrium concentrations of PB plus 2 and I minus 2. Okay, so what we did with this problem for number 2 was we identified the equation, we did an ice table, and we understand that PbI2 is a solid and it is not factored into our equilibrium expression. And once we established our, X and 2x for PbI2 in terms of their values, we plug them into our KSP equation, which we have right here. Now, KSP being provided, we were just plugging that in, and then the x and 2x are what we gathered from the ice table, okay? We did some fancy algebraic work here, and we were able to come to the conclusion that x equals 0.0012, and x is representative of the Pb ions, so the molar concentration of your lead ions. So then that means since just iodine is having a 2x, you would just take that x value and times it by 2 to get the molar concentration of iodine, which is 0.0024. Okay, so that's a recap of number 2. Now, in any of our KSP problems, you're either solving for KSP or you're solving for a molar concentration. The previous one, they were asking us to solve for a molar concentration. Here, we're solving for KSP when you look all the way down at 3C. Okay? So the first thing we have to do is we have to find the equation for dissolving solid silver dichromate, which is Ag2Cr2O7. So I am going to write that out. Okay, it's basically a decomposition reaction. Okay, we identified charges, since these are now ions when they're dissolved in water. KSP is all about a solid dissolving in an aqueous solution. So we're always going to start with our solid. And then we have aqueous for our products here. Now we have to balance it, so we put a 2 in front of Ag. Okay, now in writing the KSP expression, it's the same setup that we had from the lab. So KSP equals your products over reactants. Now your products are aqueous, your reactants are solid, so we're not including the reactants. So we have Ag plus 1, and this is going to be squared because of our coefficient 2. And then we have our dichromate minus 2. Okay, now if the goal for C is to calculate KSP, we need to figure out the molar concentrations of silver and dichromate. Okay, now they do give us a clue into that within the previous part of the C's problem. It says a maximum of 3.684 times 10 to the negative third moles of Cr2O7 dissolves in 1 liter of water. Okay, so what that's telling us is the molar concentration of silver dichromate, okay, which is 0.003684 molar. All right, and all I did was just convert this, divide it by your liters of solution, which you divide by 1, so you're getting the same thing, and then I'm just getting rid of the scientific notation. Okay? Now, we want to look at an ice table to just make sure what our values are going to be for our equilibrium concentration when we plug in our X or our 2X. So we have to set up an ice table. Okay, so we take our equation, and I'm going to see if I can just grab this, duplicate it. Oh, let's try that again. Might not work. Yeah, it's not going to work. Okay, I'm going to rewrite it. So we have Ag2Cr2O7 gives us 2Ag plus 1 plus Cr2O7. Both of those are aqueous. Okay? All right, so the solid doesn't matter. It's not a part of it. And initially, since this is our initial concentrations, our products are nothing because we haven't actually dissolved the solid into the solution yet. Okay? Now, the change is contingent upon the direction that it's moving. So the silver can only go up from 0, and same with the dichromate. And this is going to go up at a rate of 2x and x, and that x and 2x is determined by the coefficient that's in front of the ion. Okay? So then our equilibrium is just going to be 2x and x. All right? Now, this value that is provided here technically represents the x value, okay? And here's an understanding that we have to come to. When Ag2Cr2O7 dissociates in water, you're going to get one dichromate for every 2 silver ions, and that's aligning with our coefficient, right? So if our silver dichromate has a molarity of 0.003684, okay, that is going to be the same molarity as something that has, the 1-to-1 ratio, right? For every 1 mole of Ag2Cr2O7, I get 1 mole of Cr2O7. So this value, in effect, represents X, right? So our second E in our ice table, X is going to equal 0.003684. Okay, now 2x would be 2 times that value. Okay, so I'm going to do a little bit of rounding here, but it's 0.0073. Okay, so with that understanding, we know our equilibrium concentrations of our products now. So it's 0.0073 and 0.003684. So now we're going to plug this back into our equation. Okay? So I'm just going to erase a little bit of the stuff over here. So Ksp, bring it down here. Oop, I think I grabbed too much. Oh, wow. All right. I'm just going to write now because I don't know, I'm picking up too much in my copying. Ag plus 1 squared Cr2O7 minus 2. Okay, and then we take our values that we just got right here and we plug them in. So silver is 0.0073 and dichromate is 0.003684. can't forget the square. And so now we calculate. Okay, so you punch this in, square first, then multiply. You get 2.71 times 10 to the negative fifth. This is your Ksp for silver dichromate. Okay? All right, I hope that helps.